Software complexity is the invisible enemy that we're constantly battling. But what is complexity, really? How can we represent it in processes and artifacts such that we can confidently eliminate complexity and streamline our software? In today's video, I will show you a three-step first principle problem-solving framework that I've distilled and how we can apply this to streamline complex software. But first, we need to see how complexity can be represented and visualized. And then, how the streamlining process works in action. My name is Derick Chen, and this is BuildWithDC. I am a software architect at Amazon Web Services, and I tackle software complexity together with my customers every day. I get airdropped into the most complex software projects in order to re-architect and help software engineers to build faster and better. In these past few years, I've gradually distilled a mental model to an approach of simplifying complexity reliably to accelerate the rate of innovation, regardless of the business scenario or the industry. It's a simple three-step approach. Step 1. Question. Criticize the problem. Model the status quo, take a deep dive, and remove all assumptions. Find out what is the most fundamental challenge that you're dealing with. Step 2. Streamline. Hit the delete button. Use your philosopher's razor. Remove processes, steps, and anything that could possibly be cut, and put things back where you have gone too far. And step 3. Optimize. Rethink the remaining solution. Are there alternatives to the current composition? What is the best way to achieve the outcomes or to carry out the streamlined set of steps? The key concept here is to challenge everything. Leave no stone unturned. There is a complexity threshold below which software engineers can comfortably iterate at speed. Recursively apply the steps until you have suppressed the software complexity to below that threshold. But that means we need a way to quantify complexity in software systems. Let's see if we can visualize complexity and see this streamlining process in action. We'll start with something simple. In this function, we're simply checking if a given number is a prime number. It only has a few branches of logic. But what if we analyze this function by the points in the execution where we need to make certain evaluations? These are known as decision points. Let's visualize the execution paths. So at every control flow statement, the if, for, while, etc., we see new execution paths emerge. These paths make up the control flow graph, which is a director graph. A node in this graph is a basic block of the program. For example, an evaluation statement. An edge is the path between two nodes if the control may be passed from the first to the second. In this example, the if-else evaluation on line 2 is a node with two outgoing edges to proceed to the for loop or to return false. This looks simple enough to us, but how do we measure the complexity so that we can compare this with another function? Cyclomatic complexity was a concept designed to quantify complexity in the program by the number of linearly independent control paths, so we can compare the level of complexity in different parts of a software. To calculate cyclomatic complexity, we take the number of edges minus the number of nodes and add 2 times the number of software components. And in this case, the cyclomatic complexity is 4. Then, what makes a particular piece of code complex? Since the cyclomatic complexity is proportional to the edges and nodes, and we can't have orphaned nodes in the control flow graph, then having too many logic blocks and variations of control paths will add to the complexity. Let's review another version of our prime number function that has a similar outcome but a more complex implementation. For the purpose of this illustration, let's not care too much about the algorithmic performance for now. The logic is similar, but instead of checking if every number smaller than the square root of the input is divisible, we're only checking the odd numbers. But this means we need to deal with the edge cases for 2 and 3 first. You already know that the second version is more complex than the first before you even read the code. The second version already takes up twice the number of lines of code. But what does the control graph say? The control graph has longer paths because we're handling the edge cases first. Let's compare the control graphs of the two versions of this function and the resulting complexity. The second version of the complex prime number function has a total complexity value of 7, almost twice as much as the simple version. Does that mean that we should refactor this function? Not necessarily. The creator of cyclomatic complexity did give a ballpark correlation between cyclomatic complexity value and the level of risk in the software. But in my opinion, this needs to be contextualized. If you want to be really methodical about this, then take a function that you personally find too complicated to modify or add new features to, and calculate the cyclomatic complexity value. This can act as the complexity threshold I mentioned earlier to guide you if you need to further refactor a given program. It is likely that as you become more experienced and more familiar with the repo or the stack, your personal complexity threshold will increase. So with our understanding of cyclomatic complexity, what can we generalize about how complexity gets introduced? Complexity is proportional to the order and size of the graph, where order is the number of nodes and size is the number of edges in the graph. Then the amount of complexity in a single software component can be raised when new evaluation statements are added, which invites additional control paths. The correlation between the increment of nodes and edges is not linear. There's a localized network effect on the complexity in this graph, and the resulting complexity increase at scale is typically the square of the number of new nodes being introduced. As the complexity increases, it becomes harder for us to capture the nuances, modify, and build on confidently. So how can we use the complexity streamlining framework to reduce complexity? Step 1. Question. We first assess the situation, establish how different parts of the software work together, how they're communicating and passing data. And we uncover the missing knowledge. Next, we scrutinize the challenge we have at hand and identify the root cause. Then in step 2, we try to streamline the solution, remove redundant executions, and rewire the existing layout and design within each software component. We have to be bold to delete more than we think we should in the beginning, and put back the mission-critical parts to discover the minimally viable solution. And lastly, in step 3, we challenge the solution so far. How can we group functions and modules to minimize cross-component communication and variations in the control paths? Is there another perspective we can use to distill the solution that will result in a simpler model? Now that you are introduced to the strategic approach to reduce complexity, there are more specific tactics for each layer of the software, and I will share more in-depth walkthroughs, resources, and guides in the upcoming videos, so don't forget to subscribe. In summary, we can represent and visualize complexity with nodes and edges in a directed graph for our software. Complexity is proportional to the unique execution paths, nodes, and edges within a component of the software. There is a baseline of complexity within a software component that we can manage confidently, and beyond which we need to consider refactoring. We have only explored complexity in software programs so far. The architectures that we are working with today are far more complex. In the following video, We will extend this view of complexity to higher order architecture and explore how to handle complexity at different levels of the software. This will eventually help us achieve adaptiveness in our software systems and allow us to innovate faster. I hope you've enjoyed this video. Please remember to like, comment, and subscribe to this channel as we explore how to build complex software systems better and faster together. My name is Derick Chen. Thank you for watching and see you in the next video.